Hello, everybody. Thank you for joining us in our presentation today. My name is Christian Minegra. I'm a mechanical engineer with Fuji Poly America Corporation. Today, we're doing a pre-recorded presentation on our dispensable materials. We'll be following the presentation with a questions and answer session. Please, if you could write in any questions you might have on the right side of your screen. There should be a chat and a Q&A section. We'll be monitoring those. We also have a few handouts available. There's a PDF version of the presentation as well as our SARCON guide. And so I'll be playing a pre-recorded video. It's about 18 minutes long, and then we could take as much time as we need on the question and answer session. So please feel free to ask any questions that might be on your mind. Thank you very much, and I'll begin the presentation now. Hi, everyone. Thank you for joining Fuji Poly for this webinar today. My name is Christian Minegra, and I'm an engineer with Fuji Poly based out of our North American headquarters in Carteret, New Jersey. Today, we'll be discussing dispensable thermal interface materials. Dispensable thermal interface materials have been around for a long time, especially in the form of thermal greases, but they've been more widely adopted for massive use in recent years. So today, we're going to talk about some of what those materials are, the different types of materials, different types of applications and use, and even some of the equipment which is used to dispense these materials. It manufactures a wide variety of thermal interface materials. The total market for solid gap filling pads and thin films is still greater than the dispensables, but we expect the gap to continue to close. The addressable market for TIMs keeps growing quickly due to the expansive nature of electronics in our lives. The number of electronic systems we interact with on the daily is increasing dramatically. Many companies have been looking to reduce the number of registered materials and simplify their BOMs. Thermal interface materials can help in that respect because the same material could be used across applications without needing to create or source new parts. Process and manufacturing engineers simply need to identify the best methods of application and optimize the volume or weight of material required for each component. Before we continue, I'd like to give the definition of a dispensable TIM. It is defined as a compound having a low enough viscosity that allows it to be pumped through the nozzle of a syringe, cartridge, or valve. Most of the materials are also thixotropic, so that they hold their shape or appear fairly solid until a sufficiently large shear stress causes its viscosity to fall and allows for material to flow. Form-in-place material is our most popular type of dispensable TIM. We have our SPG series of silicone-based, and these are ranging from 2 watt per meter Kelvin all the way up to our brand new SPG 70A, which is a 7 watt per meter Kelvin material. So the form-in-place materials are gap-filling gels. They tend to have a higher viscosity, and they have a high concentration of fillers to give them that high thermal conductivity. We also have a brand new line of silicone-free form-in-place material. Right now, the SPG-25B and S is our latest product to be released, but we do plan on having a 4 and a 5 watt per meter Kelvin material coming up in the near future. And the reason for silicone is primarily because of some optical applications. Anybody using silicone lenses would like to possibly avoid silicone contamination and a few other niche applications. It also gives us some more flexibility on the composition of the materials. We might be able to make some of the non-silicone materials have properties that we don't with the silicone types, which have already been established. So we're pretty excited about that. Then we have our 2-part gap fillers. So this is basically an RTV, or room temperature vulcanizing system. It's a 1-to-1 mixing ratio. So you'd get these in a dual cartridge type of setup, and they have a conductivity of 2.3 and 3.0 watt per meter Kelvin. And finally, we have our tried and true thermal greases. Like I said, thermal grease has been around for a long time. We have a wide range from 0.7, which is pretty standard stuff, pretty standard heat sink compound, all the way up to our SG50 and 60NS, which is on the higher end of the scale. And so the greases still have their spot, especially in very high power semiconductors, which really, you can't really beat the thermal resistance on a grease when you have a thin bond line of under 3 or 4 mils. You just can't really get a thermal resistance down that low with a solid gap filling pad. So that about summed up the variety of dispensable materials that we have to offer. Now, they're applicable to both thin bond lines and gap filling applications. The uses are going to vary and the material selection is dependent on system designs. For example, a thermal grease would not be used in a gap filling application. Each formulation has some unique characteristics that will impact recommended bond lines and flow rates. And we do have a very wide variety of materials as you've seen. So it's always best to reach out to your Fuji Poly technical contact for support with material selection. A minute ago, I mentioned both gap filling and thin film, thin bond line applications. So in a gap filling application, the material is applied on the component level, and there will generally be a fixed space due to the board topography and mechanical tolerance stack-ups. The dispensable gels and RTVs offer the advantage of low insertion force relative to their counterpart in the gap filler pad family. And that might actually be the driving factor when deciding to use a dispensable gap filler. Even though we do make some extremely soft gap filling pads, right? PCB deflection specifications and fastening limitations, right? The number of places where you can place your fasteners, those often pose design problems, and a lot of times you'll have to turn to a dispensable soft material to solve that. The maximum gaps for dispensable materials will vary depending on their viscosities, how sticky they are, whether it's a vertical or a horizontal orientation, and whether they vulcanize or if they will remain in gel form. We always recommend thoroughly testing the stability of the material in each given application because everybody has different circumstances and the material might behave differently from one application to another. The thin bond line applications, on the other hand, often have no gap to fill or perhaps just some roughness and flatness to deal with that does not require material gap filling. At bond lines under 5 mils of conductivity is less an indicator of performance than the final bond line, and the material's ability to spread over the interfacing surfaces. Fixed clamping features such as springs, screws, and clips are typical. The material should be easily spreadable but stable enough to prevent pumping out. In either case, material performance and durability is important, so Fuji Poly can provide test results which include testing of thermal resistance, thermal conductivity, viscosity, compression loads, and durability to heat shock, low and high temperatures, and high humidity over time. To speak a little more about the dispensable gap filler applications, there are two types of dispensable gap fillers. One would be the curing types, and they come in the form of a two-part 1-to-1 mixing ratio. They're typically room temperature vulcanizing or RTV, and can cure with and the cure can be accelerated with higher temperatures. The non-curing types do not require a curing schedule, as the compound will not have any additional reactions after we manufacture it. They are not volatile. These are stable materials that will undergo little to no chemical change after being dispensed. Two-part materials, of course, require mixing through a static mixer, and there's a pot life associated with the material after mixing. The dispensing system will have to work with the dual cartridge packaging, or it will have to be pumped from two separate pails and combined through a mixer, and then finally out of a valve. The non-curing types are ready to use immediately and require no mixing. For thin bond line applications, the most common dispensable material is thermal grease. Thermal greases come with different viscosities and thermal conductivities. They can be dispensed from a syringe, painted on with a brush or roller, or even screen printed. The screen printing or extremely thin bond lines might require that a solvent be added to the grease so that it could spread more easily or pass through the screens more easily. The solvents would evaporate at room temperature, and the greases do not require any elevated temperatures or curing. Now, some manufacturers and engineers dislike using thermal grease, and so there are solid alternatives like thin film silicones, thin gap fillers, and phase change, but it's difficult to get the same performance of the grease, especially if your bond line is under 100 microns. So the greases definitely still have their place in the industry. There are both manufacturing and design factors which influence the decision to use dispensable thermal interface materials. Automated manufacturing is highlighted more than ever with employee shortages we have experienced within the past 2 years. While solid gap filler pads can be placed robotically, it can be challenging to design these systems to pick the materials consistently and in a timely fashion. Dispensable systems, on the other hand, have been commonly found in large manufacturing facilities for a long time. They are commonly used for coatings and adhesives, but the same robotic systems can typically be used for dispensing thermal interface material. Bill of materials simplification and reduction of part numbers is also a benefit to high volume manufacturing and assembly. A single dispensable TIM can be used across many programs with a single part number and would only require the exact material weight per unit or component and takt time specifications to be set. Next, I'll take some time to discuss packaging options, dispensing equipment, and we will look at a few videos we recorded with one of our manufacturers to illustrate the equipment dispensing the materials. There are numerous package sizes and packaging manufacturers to choose from. Some dispensing equipment requires the packaging to be compatible with their systems. Fuji Poly can basically implement most package types on a case-by-case basis or as needed. Our standard packaging is typically 10 cc and 30 cc syringes or 1 kilogram jars for thermal greases. 2-part gap fillers require a dual cartridge, so you'll get it as a kit, which can be anywhere from 50 cc's, so you have like 25 of the part A, 25 of the part B, potentially up to like about 400 cc's as a cartridge kit. And then larger than this would have to be supplied in individual pails. The cartridges will have a mechanism at the tip for attaching a static mixer for the material to thoroughly mix before being dispensed onto the component. Our non-curing gap fillers typically come in 30 cc syringes, 1 kilogram caulk tubes, or cartridges ranging from about 6 ounces up to 20 ounces. We also supply 1 gallon or 5 gallon / 20 liter straight wall pails for use with a high pressure hydraulic pumping system. These systems have a ram press which will directly pump material from the pails. Dispensing equipment range anywhere from a simple controller with a compressed air line to a tabletop system or a large pass-through robotic dispensing cell for use on a production line. The smaller systems are pneumatically driven and controlled by time and pressure. These are ideal for lab environments or for small production runs. Obviously, there's a big jump from just having a simple controller hooked up to an airline to having a tabletop unit where at least potentially given the surface area, an operator could place more than one device, run the program, and step away for some time. The larger units typically use a separate hydraulic pump to feed material out of a pail over to the specialized valve in the robotic dispensing cell. Various types of tips or nozzles may be used when dispensing the material. The components are usually carbide to prevent damage by the abrasive thermally conductive fillers within the TIMs. This diagram depicts the hydraulic pumping unit. They usually have a pail clamp to reinforce the steel pails and keep them from bursting under high pressures. The material will be fed through the ram and high pressure hose to the valve mounted in the robotic dispensing cell. Some of the challenges in high volume production include the volume consistency per shot. Because these are heavily filled materials, it's common to have some flow rate variation within the package and in between lots. Storage conditions and material temperature upon dispensing can also have a large impact on the flow rate. There are specialized valves available to assist with some of the dispensing difficulties. One example would be the snuffback high pressure valve manufactured by PVA, which has a large diameter chamber. It has the highest flow rate. It uses time and pressure to dispense a given amount. You could program it to dispense a different volume over a number of different components, and it creates a pullback so that the material does not ooze after the dispensing is done. For smaller shots or if a more consistent volume-based dispensing amount is required, then there are lower pressure valves that work with cartridge systems. There are positive displacement and positive cavity types, which can more accurately dispense material while sacrificing maximum volume and dispensing rate, right? So you could either have a fixed volume chamber that will be dispensed, that you couldn't adjust the volume of material being dispensed on the fly, or you could have a positive displacement, like a kind of almost like a screw type dispenser. But again, the maximum volume and the flow rate will be limited compared to the, the pass-through snuff back valve. This video was taken using a PVA Delta 6 robotic dispensing machine. And the material is our SPG70A. It's a 7 watt per meter Kelvin, high thermal conductivity, non-curing gel.
Good? Yeah, we're good.
Questions regarding the optimal dispensing patterns come up regularly. Is one pattern better than another? Is a bead better than a Hershey kiss? Do I need to cover the entire component? The area the TIM is intended, the area that the TIM is intended to cover and the thickness of the gap is obviously a key consideration. And you'd like to cover as much of that area as possible to make sure that you have the best heat transfer available. It's better to keep the material close by when you're dispensing. If you have like a larger surface area and you need to dispense some kind of a pattern rather than just like a blob in the center, you'd be better off keeping the pattern tight so that you don't introduce too much air, because air will impact the heat transfer. For small components, the Hershey Kiss is the most commonly used. There's little chance of air being introduced, and it's quick to dispense. Rectangular or square surfaces might require a pattern of beads, such as that seen in the videos that I had just shown. And that will wrap up the presentations for today. Thank you everyone for attending. If there are any questions or any need for data, we look forward to engaging with you and helping in any way possible. We have a manufacturing center and technical support in New Jersey. We also have 2 engineers in our San Jose Customer Engineering Resource Center. They have a lot of nice test equipment, and they're there to support the local market, but also to serve the needs of any customer which may require their talents. Please feel free to send us an email as shown on the screen to info@fujipoly.com or to fpcerc.com. And don't forget to check out our website, www.fujipoly.com, for all of the latest data, technical information. And we also have plenty of content on our YouTube channel, so please check us out there. And we'll now be going into our questions and answer session following this in just a moment. Thank you. All right, thank you for listening, everybody. I hope it was informative. Please feel free to go into the Q&A section and put any questions that you may have. I have a few already that I'll just go ahead and jump into them. And just a reminder, anybody who had some technical difficulties, we apologize. I will be posting a recording of this session on our YouTube channel, and we have a lot of great content on there, so please go check it out when you have a chance. First question, what's the best way to select the amount and dispensing pattern for different surface areas and thicknesses? And is there a software we can use? I'll answer the second part of the question first. That I know of, there's no software that can be used to automatically determine the best dispensing pattern. If the material is being dispensed robotically, obviously it's like a CNC coding, G code usually. which is used to program the robotics. And at that point, I would actually think that maybe the equipment supplier could maybe provide some input and provide some assistance. They're usually pretty knowledgeable about those kinds of things. But as a general rule, and there's one thing is the volume of material to dispense, and that's fairly straightforward. You would take your nominal gap and the surface area. So multiply the gap in the surface area, take some tolerances into consideration, and that should be the volume that you need to dispense. As far as the pattern is going to be dependent on the surface area. The larger the surface area, obviously you're not going to be able to get away with like a smaller blob or Hershey's Kiss along the center. You may need to, do kind of like the square pattern or go around in different shapes. But it's really on a case by case basis. You could feel free to share some more detailed information with us, and we'd be happy to give you our input. Any of your TIMs have adhesive properties? So none of our materials are actually structural adhesives. They do have, all thermal interface material to a certain extent does have some adhesive property because that's the way that it works. It's intended to wet out into the surfaces, fill in any air gaps and micro gaps, and there is actually an adhesive bond that's formed between the substrate and the thermal interface material. And the two-part materials that cure in place tend to have a little bit more adhesion, but they're in no way any kind of structural adhesive. Okay, can this be custom packaged into different size cartridges? So our most common packages would be like 30 cc. We do a lot of cartridges like 1 kilogram cartridges. A lot of customers like to use Semco or Nordson. Really, anything that's required for dispensing purposes, we could take a look at packaging for you. But yeah, 30 cc and the cartridges, and then 1 gallon or 20-liter pails are probably the most common. But we could look at anything on a case by case basis. Okay, is vibration a consideration for the cure and paste dispensable TIMs? Is there a chance that the TIM separates from the heat source since there's no pressure on the parts after the TIM is cured? Right, so that's a good consideration because, like you said, the insertion force while the TIM is a liquid is basically zero, and then it's curing in place. Now, what you do have is what I just mentioned, that adhesion that's formed between the TIM and the substrate, which allows it to expand and contract under vibration. Now, I'd say the larger that the gap, maybe the more concern that you need to have with the vibration, just because there's more room for everything to move around. But generally, we put these materials to durability testing, high and low temperature, shock, and things like that, and they'll hold up fairly well just because of that adhesive property, whether it's a cured material that cures in place, or a single component gel. But a lot of it does depend on the gap size, on the orientation, and different things like that. So it really, every application is unique and needs to be vigorously tested, and if there's any concern with vibration or gap size. Does automated dispensing have benefits for controlling thickness variation over thin tin pads like 1 millimeter? Um, for controlling thickness variation over thin tin pads like 1 millimeter. So I guess the I'm not sure if the question is more about like the compression loads or the uniformity of dispensing the material. When you're dispensing it automatically, you could change the amount of material in any given location. So I guess that's one thing that would benefit it rather than just having a gap pad that's a millimeter thick gap pad. Uh, but yeah, maybe we could talk some more and clarify later on your question. Can the machine dispense different thicknesses to cover different gaps, such components and heights? Yeah, especially the type that's just controlled by time, right? So depending on how much material, you have a fixed load, I mean a fixed pressure at the nozzle, and then you just for every location you could control the amount of time that the valve opens and lets material flow, and that'll control the volume or the stack height. So yes, you could actually change, adjust the gaps in component heights for the with the amount of material. If using thermal grease in a shock and vibe environment, are there any considerations you would suggest? Is there a risk of grease flowing out? So yeah, there's always a risk of the thermal grease, some of the thermal grease is pumping out. Specifically, the lower performance and lower viscosity greases tend to have more of a risk. That's why you'll see as we go up in the thermal performance on the greases, they also become higher in viscosity. But we do maintain a high level of tackiness in our product and a low amount of. You might also have some solvents in there to help it spread better. So the tackiness and the viscosity are going to be a big consideration for a thermal grease and the risk of pump out. So definitely you'd like to look at those two parameters, how viscous and how sticky is the material and what kind of gap you have. Okay, for non-curable dispensable TIMs, do you have any materials that can maintain performance in vacuum? So we do test all of our SPG form and place materials to the NASA's ASTM E595 standard, which checks for outgassing, total mass loss, and water vapor absorption or something like that. So yeah, they all are rated for space and for use in vacuum, as well as our gap pads. We use a very high quality silicone base, which has a low volatility to it. So in that respect, it should perform well in vacuum. I don't know if there's any existing space applications. I'd have to look a little bit more into that. I know we have plenty of our gap filler pads in aerospace applications, so I'm not so sure about the dispensable materials, but I'll be happy to look into it for you. Okay. What are the upper temperature limits? Generally, up to 150 degrees Celsius for most materials. Some go a little bit higher. I mean, there's a difference between recommended operating temperature, which will recommend up to 150. Maximum might go up towards like 200 degrees Celsius, but it's never recommended for long-term exposure at those kinds of temperatures. I'm just going to switch over to the other chat tab because it looks like there might be a couple of questions in there that I hadn't been looking at. Okay. What is the typical lifetime of the TIM? So the lifetime, once dispensed and in the application, I mean, it's pretty. Usually, it'll be longer than the life of any product that it might be in. Some of the things that might shorten the lifetime is the temperature. If you're going outside of our recommended operating temperature, specifically on the high end of the temperature range, that could impact the tin by creating hardness, increased hardness, or drying it out a little bit. So that's something to keep in mind. But generally, I mean, the silicone or even the non-silicone compounds themselves, they don't break down very easily and they're very long-lived. The two-part gap fillers have been mentioned as being volatile. So does that mean they outgas during cure? So during the vulcanizing process, there is a chemical reaction. I don't know specifically what level of outgassing during the process. I don't know if we've ever actually been able to measure that. But yeah, any chemical reaction does have its byproducts. It could be heat. It could be an outgassing of some form. I'll see if I can find out more information on that, but I don't know specifically. Okay. Okay. Do you expect the thermal performance to degrade quickly over time comparing to thermal gases? Not necessarily. You know, I think both of them could perform well for a very long time. The thermal grease, obviously, you do have the risk of pump out. So things like shock, big temperature swings, vibration might cause the greases to degrade a little bit more quickly than a standard material. So there's that to keep in mind. Between gap pads and dispensable TIMs, which one is more commonly used? So as far as the broader market, I think the gap pads are still more widely used, but the dispensable TIMs have been catching up. For Fuji Poly, our solid offerings, I mean, we have a lot of gap filler pads and thin film materials, extruded materials is still the by far the larger part of our business. But there definitely has been a move towards more dispensable materials. I could say that much, and it seems to me like you know the, the the balance between the two is starting to even out. Whereas it used to be by and large gap filler pads and very few dispensable materials, but I think that gap is closing. Okay, and I think I might have gotten most of them. In the chat, I see two more questions in the chat. If I have components that might be subject to movement in use, is a gap pad better or a form in place option generally preferable? So our form in place materials are actually used in automotive applications, for example, fairly high vibration applications. Um, I think depending on the gap size, we might recommend using a solid thermal pad instead. We have to look at it, but generally, I mean, if the gap is under, like, let's say, 1.5 mm, the form in place is very robust. If you need to have a gap larger than that, then you might want to consider a solid material for sure. Are the gap filler pads affected by material shortage? So what are the lead times? Okay, that's a good question. We did have some materials, certain materials affected by material shortages, specifically, some of the base materials for these. I think now I like to say that that's pretty much been taken care of, and we're not having any capacity issues at the moment. We know some of our customers are still a little bit constrained, and they're not getting the productivity that they need. That might be more related to raw materials and semiconductors and things like that. But on our end, I think we've gotten over any shortages that we were experiencing. And how do you evaluate the optimal dispense patterns to determine if air is entrapped? So, I mean, if you're dispensing two patterns with air in between them, like this is a little bit hard to picture, but any air between two dispense patterns after compression could possibly trap air. So if you're going to create a pattern from the center out, or something like that, to fill in a whole area, you'd like to get the beads close together. The further the beads are apart from each other, the more the potential for trapping air. So you'd like to keep adjacent beads touching or nearly touching, I think. Fujipali could certainly provide samples. Please feel free to contact us, and we'll be more than happy to get you. We usually hand out a couple of 10 cc syringes to anybody who needs them. We could also, do other types of sample arrangements if you need them. Please feel free to contact us. And I think that just about wraps it up. We're a little bit over 30 minutes now, so I'm going to again thank everybody for joining us. You had a lot of good questions for us. We hope this was informative. I'll be putting a copy of this on our YouTube channel. I've put recently. I put some new videos on there, especially if anybody who's interested in automating the placement of gap pad materials or dispensable materials. There's a new video on there that you'd probably like to check out. And again, thank you everybody for joining us, and we hope that you have a wonderful day. Take care.